So, Yuri, okay, recording in progress, and you can start your talk.
Okay. So thank you for invitation. And I will talk about growing Young diagrams. So I will explain what it is for those who do not know. So it deals with integer partitions. So we call some sequence of non-negative integers which sum up to n. We call it a partition of n, and we do not take care about order. So we can choose any order we like, and it is common to choose a decreasing order, so that these summands, which are called parts, are decreasing. And I will denote the set of all partitions by P of n, and it is a set of all partitions of n. And by P, I will denote the set of all partitions. And it is natural and very useful to consider the following graphical representation of a Young diagram. So I just give an example. I'm not giving a formal definition, but it should be clear from this example. So suppose we have a partition of say 12, which is 4 plus 3 plus 3 plus 1 and plus 1. Hopefully I haven't done any mistake here. And then we can denote this partition in at least four different ways. So either we can just list these parts, or we can adjust this, prolong this list by an infinite sequence of zeros, or other way to list is to count how many times each part enters our partition. So we skip zero counts. So this notation means that 1 is presented twice in our partitions, and 3 is also presented twice, and there is 1 4, and we don't write power 4, power 1. As usual. And so this number of parts k is important for us, so we shall denote it by ck. So it's count of parts k in a partition lambda. So in this example, we have I wrote these numbers, and so what is Young diagram? It is some collection of boxes which are arranged in a picture like this. So so if we have the largest part, we take a row of boxes. So these are supposed to be unit square. So it has, the first row has area 4. And then we take next part, and we arrange it, we place that many boxes in a row, and we put it over the first row and align it to the left, and so on. So it's more or less, I believe it more or less clear for those who didn't know this notion. And these partitions can be arranged in the so-called Young graph. It's a graph which is which has partitions as its vertices, and edges are drawn if you can between two partitions, if you can obtain one from another by adding or removing a box from the Young the corresponding Young diagrams. And these partitions are naturally arranged in levels, so which are just the weight of partition of the size of partition and or the area of Young diagram. And here I drawn the first 5 or 6, maybe because we number levels from 0, first 6 levels of the Young graph, and the corresponding number of vertices in each level. And this number of vertices is usually denoted P of n. It's number of partitions of integer n, and its generating function is well known since earlier. So and I actually want to give a short proof of this fact. So let us consider this generating function, and then we can first we can write this weight n as this linear combination of not cycle part counts, and then instead of summing over levels, we can sum over all partitions which are present. Then level n, so this will be n if lambda is a partition of n, and it will be counted with p of n times. And then this q to this sum, power of this sum, we can write as product of q to the just one summand. And then we can replace sum over all partitions by sum over all possible values of cycle counts, or sorry, part counts. And if we do it, our infinite sum will can be written as an infinite product. And then, in order to take to obtain q to the power n from this sum, we should take some q to some power from the first parenthesis, which is 1 times r1, and then q to some power from the next parenthesis, and it is here we have all powers divisible by 2, so it's 2r2 and so on. And then in order to have q to the power n, we just need that this sum of powers taken sum up to n. So from starting from certain point, we have to take just one from all parentheses, and then this can be written in this compact form, and the series converges for q less than absolute values than 1. So when we had this Young graph, then an edge means that we can just add some box, and if we have a partition, we have many possibilities for adding a box. And if we start from an empty diagram which has no boxes at all, and then we add some boxes in certain according to certain rule, and if we add n boxes, then we come up with a partition of n, and we can do it in some deterministic way, but actually it corresponds to a path of this Young graph. This adding procedure of adding a box corresponds to a path which ends up in certain partition on level n after n boxes are added. And I will talk about a stochastic way of adding boxes. And so in this example, we have 4 possibilities. So we need 4 probabilities that sum up to 1, and we add a box in different places with different with corresponding probability. And actually, we can do it looking on the path by which we came to this particular partition, but usually it is done in some Markov way. So it means that this probabilities depends just on this shape of this partition, or shape of its Young diagram, but doesn't depend, do not depend on the way we came to this probabilities. And then we can just say about a random walk on the Young graph in each in each step. We just have assigned some probabilities to these edges which come from each particular vertex, and we go down with this probability. So it's a kind of random walk. So I will give you 2 well-known examples. The first is the so-called Euwen's measure. So it is as follows. So to each partition we can add a new part 1, and we do it with probability which depends just on the number of boxes or the size of partition in such a way where theta is some positive parameter. And otherwise, if we do not add this 1, which is represented by this box, we should add some one of these 3 boxes, and we do it by the following simple procedure. So we drop, we take at random uniformly one of n boxes in this diagram. And so suppose we took, can you see my mouse, by the way? I'm trying to.
Yes, we can.
Yes.
Okay, great. So suppose we choose this one, and then we increase this part, but we cannot place a box here, so we place it here. And it means that probability of increasing this box will be 6, and it is not so here I wrote non-conditional probability, so it's total probability that we didn't add this but add this. So conditional probability will be just 1/2 to add this, but total probability will be 6/12 plus theta. And it is well known that this procedure, if we follow this procedure, then on level n we can write down an explicit formula for probability to end up at this specific partition lambda. And actually this this measure has nice combinatorial interpretation, because if at least if theta equal to 1, then this will be a measure which is obtained from the uniform random permutation of n objects. So we take each permutation with probability 1/n factorial, and then we look on cycle structure of this permutation, and it gives naturally a partition of n, and this is exactly the same measure. And actually this procedure can be further generalized, but I won't talk about it. And another example I wanted to mention is the so-called Plancherel measure. So this here the formula for probabilities is somewhat not that simple as in the previous case, but it's still very explicit. So we can first we can rotate our partition by 45 degrees, starting from the way I oriented it in the beginning. So we took this new coordinate system, which is in blue, and then there are upper inner corners of our partition and upper corners, and we denote the coordinates by x0. By axis we denote coordinates of inner corners, and by y's we denote coordinates of upper corners. And it is easy to see that they just interlace. So there is one more inner corner than upper corner, and they are oriented in this way. So, and then we consider the following function of z of z, and this is a ratio of two polynomials, and then we can just decompose it into simple as a sum of simple fractions, and it is just by multiplying by z, we see that the sum of these alphas is equal to 1 after letting z to infinity. Then the left hand side goes to 1, and the right hand side goes to sum of alphas. Somewhat less obvious but still true is that all these alphas will be positive, or at least non-negative, and it is actually the it follows from the fact that these two sequences interlace, and I just calculated alphas in this specific example to show you that it's not they are not so obvious. They have not very obvious values, but and anyway, you can do it. And then on measure on level n, we will have this measure which is done as Plancherel measure. It's just has the following formula here. Dim lambda is the so-called dimension of a partition lambda, and it corresponds to a dimension. So partitions, among other things, partitions in index irreducible representations of symmetric groups, and this dimension is the dimension of the corresponding representation, and it also has a simple combinatorial interpretation. It's just a number of paths which end up at partition lambda in the Young graph and start at empty partition. Passes of length n the number of them is this dimension. And actually, I just want to mention that this so-called Russian orientation, rotated by 45 degrees of Young diagram, allows to establish a connection between partitions and actually growing partitions and systems of particles which move to the right if partition grows, and it is illustrated by this figure. So we just take on, so we have in this upper bound of this Young diagram rotated, we have some segments which go down and some goes up, and we mark each segment which goes down by a point, and then we project these points on the horizontal axis, and it will give us some system of empty or occupied places. So I suppose that red are occupied and white are empty. And then if we add a box, then it corresponds in this terms, in terms of these particles, it corresponds that one particle moves just to the right, and we can add a box just if the next position was empty. So it's just some system of particles which move to the right. On each step, one particle moves, and and it can move if the corresponding place is empty. There are no stacks of particles here. And so this simple picture establishes connection of these growing partitions to some procedures of other mathematical physics and so on. So I won't talk about it, just wanted to mention it to somehow connect my talk to integrable systems. And so what we are interested in are uniform measures on levels of the Young graph. And actually it is quite surprising, but no process is known which leads to the uniform measure. And actually it isn't even known if we can construct such a process. And there is a theorem from different area of mathematics, from linear programming, which tells us when we can construct and when we cannot. So it tells us that if we have some sequence of measures on levels of the Young diagram, we can construct such a probabilistic Markov procedure which transfers one measure on level n to another measure on level n+1 if the following inequality holds for each subset of n, and this a with an upper arrow means the set of partitions of level n+1, which can be reached from some partition on level n from A. So this is seems very simple condition, but I tried to prove that it actually holds for uniform measures, but I didn't succeed. Actually, I still do not know if we can construct some procedure of a type I described before. And so actually, this led to idea of different type of growth of Young diagrams. And to describe it, I will briefly recall you the construction of Fristed, who proposed the following trick how we can study these uniform measures on partitions. And the trick is as follows. So instead of considering a measure on fixed level, let us consider a measure on whole graph, but which is concentrated in some neighborhood of the level we are interested in. And so we do it as follows. So we just assign a weight q to the power size of partition to each partition lambda, where q is some parameter from 0 and 1, and then we normalize it by this probability, this generating function or partition function to get a probability measure. So for each q we get some probability measure, and no matter what q is, it has these two properties. First is that the conditional measure on levels is on each level is uniform. So so it just follows because all weights of all partitions are the same on level. And another property is that part counts become independent, and moreover they have geometric distribution, which is recalled here. So it is just follows from this product representation of this generating function, which I explained to you a few slides before. So and now we have some family of measures. We have a free parameter q here, and then the idea of Fristed was to choose this q dependent on n, so that this measures p somehow behaves like measures we are interested in, that is mn, and I should have written this uni, so it's a uniform measure. And so my idea was that we can actually construct family of processes, or maybe partition valued process in which this parameter Q of free-state construction is is treated like a varying parameter which plays a role of time. And so we can actually use this parameter Q as time, but for me it is it seems that things becomes simpler if we change a variable we denote Q by e to the power minus t. Then since Q is between 0 and 1, we have that t is bigger than 0. And now we shall construct family of distribution of processes of this independent of this time t, such that we can construct a partition from with this free-state distribution. So a partition which at time t has free-state distribution with this parameter q, which is e to the power minus t. And the construction is very simple. So let us consider an array of exponential random variables, and it means that the density is just exponent with negative e to the power minus t, and then we define the process rho k of t as minimal number of such that epsilon, the second index r plus 1 becomes less than kt. So two indexes are needed here. So for each t, we can do it, and actually it is from the very definition, it follows that this as a function of t, this function okay. So I wrote decrease, but it should be doesn't increase. So it's weakly decreasing function, and moreover, for different cases, processes are independent, and also they have the geometric distribution. So because you need R these exponential random variables be bigger than kt first, and then the next less than kt. So this is a probability that that this happens, and this is a probability that this doesn't happen for smaller r. And so, and then we define partition lambda of t. So it's just now it is a partition valued random process by the requirement that these are k counts parts of parts k in our random partition. And just from construction, we have that this at each fixed moment t, this partition has this free-state distribution p minus t, and it partition decrease. So if we consider some bigger, some later moment of time, then partition will be so it means that the corresponding Young diagrams are contained one inside it the other. And actually this partition valued process which we defined is a Markov chain. And in order to make it classical Markov chain, which should have some initial distribution, we shouldn't cannot start it from zero, from time zero, because lambda of zero isn't defined at all. But we can start it from any fixed moment tau. And then it has then it has the following properties. So it should be e minus tau here. It's a misprint. Lambda of tau has this distribution, so it's an initial distribution, and then we can calculate a probability that for some small number h, our process changes from some partition lambda to some partition mu, which is which can be actually equal to lambda. So, and it has the following properties that just one part counts becomes less in mu, and all others are the same. So we just, to put it in words, we just removed certain number of parts k in our partition lambda. Maybe we removed nothing, then lambda is mu. And to see this formula, it is quite easy. So if actually mu is lambda, then it means that all these exponential random variables are bigger than t plus h. So for all k, sorry, it's also, so here it also should be not rk but r kappa, this kappa. So if lambda is mu, then it means that no changes has been made in between t and t plus h, and actually we can easily see that this happens with this probability. And if r is less than k, so we actually removed some number of parts, then we should specify there should be one epsilon exactly with the index r plus 1 between t and t plus h, and others should be either bigger than t or bigger than t plus h. And finally, in order to have lambda, the next should be the one of them should be less than t, and then just writing down these probabilities, and you immediately see that these formulas hold, and actually this is a condition for this process to be a continuous time Markov chain. So how does it behave? It starts at some random partition lambda of tau, and then it decreases. So somehow melts some of parts in this partition just disappear after certain time, and so actually it goes over over levels. So it unlike the this adding a box or removing a box, how we speaking about removing parts from partitions, but so removing a box moves us to the previous level, but our procedure removing certain number of equal parts moves us across many levels. So the probability to visit some partition will be actually comprised from two probabilities that we first we visit this level, and then on this level we visit this specific partition lambda. And actually it's there is a simple formula for this probability, so it's just this integral, and what we see from this formula is that given our process visits some level n of the Young graph, it can go through any partition of this level, but it goes actually from uniformly chosen partition, because this probability doesn't depend on lambda, it depends just on n. And actually we can this process lambda of t is defined actually for any t bigger than 0. We just, in order to have Markov chain, we want to have some initial distribution. Then we have to fix some positive tau and start at that moment. But if we let this tau to 0, then actually these probabilities have a limit. And so there are two formulas for these limits. First is as this infinite series, and another is some closed form expression. And this infinite series representation follows immediately from what we have already seen, because it is obvious that we just have to replace tau by 0. In the previous slide, we had integral from tau, but here we start from 0 because tau goes to 0. And then we use a representation of this infinite product as an infinite sum, sign changing to sum of exponents. So so actually it's it is written as a sum from minus infinite plus infinite, but here we have dependence on k is quadratic, so this is always actually positive. So we have just negative powers of exponent here, and they come with signs either plus or minus 1, or actually there are many zeros if you write it in traditional way as a sum of exponent. And then this integral, this sum can be interchanged with integral, and integrals are explicitly taken, and this give this series expression, and that this series has this closed form. It is some complex analysis, so so it's quite standard calculation, but actually I haven't seen this formula, but I believe it is kind of exercise in analysis, in complex analysis. Okay, so let us give an alternative description of our Markov chain. So it is it behaves as follows. So it waits for some time, and then jumps to some smaller partition. And this, if we just consider this partition which it visits in order in which they are visited, it is known as a jump chain of continuous time Markov chain. And so it has somewhat simpler description, because now we have just a sequence of partitions, which is obtained as follows. So if we first take some random distribution, some random partition lambda 0, which has this free-state distribution, and given we have some partition lambda, then the next partition will be just a partition which can be obtained by removing some number of equal parts, and we remove any number of parts k with the same probability k over n and of the of lambda, so the area of the Young diagram. And so the combinatorial description is very simple. So we suppose we have some diagram lambda, and then we choose uniformly at random one box in this diagram, and it then we remove all row containing this box and all rows of the same length below it. So in this example, we first choose this black partition, black box, and remove 6 gray boxes and end up with this partition view. But initially we were interested in growing partition, and here I just told you about melting partition, so it becomes smaller and smaller. And so in order to obtain growing partition, we can do a simple procedure which is called time reversal. So we just view on our sequence of partition in opposite order, and then I will denote it with heads. And a well-known result is that if we have some Markov chain, then its time reversal will be also a Markov chain. And it will have transition probabilities which satisfy this relation. So in general, they will depend on tau. Basically, this relation means that the probability to come from partition lambda, not probability, that expected number of passes from lambda to mu in reversed chain is the same as expected number of passes from mu to lambda in the forward chain. So this G of M is just probability to get into partition mu, because it's the same for all mu, and G of N is the same for all G of so maybe I should have written lambda here and mu here to make it more more intuitive. This is the same probability we had already met. And then so here this these probabilities of reversed Markov chain, time backward Markov chain, depend on tau. But it is natural to expect, and it is indeed the case, that they have a limit as tau goes to 0. And this limit is just have this simple expression for it, but I recall that this G has this complex rather big expression for G, but it's explicit. And so we can now look on this limiting Markov chain, which is obtained from this time reversed Markov chain as tau goes to 0. And so it starts at empty partition and then evolves in the following way. So we at each step we add some number of parts k, and this number is also random. And we know explicit expression for the distribution of this pair R and K. And so in order to determine what lambda J is, we just have to know how which blocks of parts have we added to it. So it is determined by this finite sequence of random vectors. But the sequence isn't Markovian, so in order to have distribution of this, we need to know the whole sequence, but actually it depends just on the size of a partition which we have on step J. And if we add this sequence of sizes to our pairs K and R, and consider triples N, K, and R, then we will get a Markov chain, which is can be also explicitly described. So we start at some random triple, which has first coordinate 0, which corresponds to that fact that we start with empty partition. And this K0R0 is a block that we add to empty partition. And we know its distribution, so we just have to plug plug here n equals to 0, and then we get this formula. And if on some step we have some triple and KR, then the first coordinate behaves deterministically, so it just as this sum, we just add KR to the first argument, and next two elements of the triple are random, and we know explicitly its distribution. So it's again quite simple Markov procedure of constructing these triples and then building Young diagrams from these blocks, not from parts, but from blocks. We obtain Young diagram of on some level after some number of steps. And actually we can forget about these blocks and just study which sizes of our growing Young diagram, and these sizes are also behave as a Markov chain because we just add this product on each step, but we know its distribution, and we can explicitly calculate it, and then it will involve the number theoretical functions, some of divisors. So these are explicit probabilities for jump from n to n plus h. So I have to go quick, so I will skip a proof. And what I wanted to mention is that actually this is a probability distribution for each n, and it means that an infinite system of an infinite number of equalities holds. So it just the same written in and opposite way. And so it is series of equalities, but actually we can view on it in a different way. We can treat these divisor functions as unknowns, and then we will have an infinite system with infinite number of unknowns, and the matrix of the system is a Hankel matrix, so it's constant on anti-diagonals. These coefficients are constant, and I didn't manage to do it, but one can probably solve this system, and then it will give some solution to these sigmas, which are divisor functions, sum of divisor functions. So it can give some explicit expression for this sum of divisor functions. Actually, some of them are known, but I don't know if any doing that will give some new expression or some new proof for some old expression. Okay, so let me briefly mention how what can we say about this rectangle which we add to a partition when the size of partition is large. So actually the parts we add behave like square root of n. So in order to this sequence to have a limit, we have to divide it by square root of n, and then it will have such density which is written here. So it converges weakly to some continuous, some random variable with continuous distribution. And if k is proportional to square root of n, then then we will R has geometric distribution, and it is written here explicitly. And also I will need in a couple of minutes this formula that if we restrict k to be bigger than x square root of n and consider the expectation of number of parts given they are bigger than x square root of n, then we will have, without any scaling, will have some limit which will be actually a function of x. And so here c is this constant p over square root of 6. So maybe I will skip this part about Poisson point process and just will finish with with results about limit shape. So it is well known that random partition chosen with uniform measure has a limit shape, which actually means the following: that if we consider this Young diagram, so it is actually we defined it as some subset of quadrant in a plane, but we can consider its upper bound, and then it will be a function of x. And then there is a result which has been shown by temporarily using some physical argumentation, and then strictly proved by Vershik in 85, and it reads as follows. So if we scale our Young diagram by square root of n along both axes, so its area will become 1. And then its upper bound will be close to some fixed function y, which isn't random. So this is a random object, and this is deterministic, and it will be close if we step slightly from 0. This curve is given by this very nice equation. So I have a picture which illustrates this limit shape. So I believe it is a random drag. I'm not quite sure what n is in this diagram, but anyway, so this is a scaled Young diagram, and this function d of x, which is shown, is blue, and the limit shape is shown in red. And so there are some deviations, definitely, but in the limit they disappear. And so I just want to explain why the limit shape should be formed, and why it should be the same Vershik's curve using our growing partition construction. So how this value of upper bound of Young diagram at point x behaves after we perform a step of our procedure. So if we add parts that are less than x, then it just we just don't see if we consider only. So it depends just on parts bigger than x. But if we scale our diagram by square root of n, here we do scale it along x-axis, but do not scale along another axis. Then we know from the theorem I had a few slides before that this can over square root of n converts the probability that it is bigger than x converts to something some number depending on x, and so when n is large, this is close to this limiting probability, and consequently this new block changes value of this half-scaled Young diagram with approximately the same probability. And I recall you this function, and actually it means that how it is changed if the parts we have are bigger than x square root of n. So then in mean it changes by this, and after we repeat this several times, say n to the power delta times, there on average, this will be an increase, and after n to the power delta jumps, the increase will be this n time to the power delta h of x, and it can be justified just by the law of large numbers that that it will be close to this deterministic number. And but there is some cheating in this argument, because we after each step we have to rescale our Young diagram. We scale it by its size, so the size increases after each step, and so we have to rescale it again. But if we don't consider too long periods of time, so we just take this power delta to be very small, then we can neglect this. We can ignore this rescaling. Doesn't mean much. So in order to study this process in more detail, let us introduce the following operator. So it acts on functions y, which has unit integral, and it adds r times some deterministic function h to y, and then rescales everything along both axes in equal manner, so that the integral of this new function y plus rh is again 1. And so we just have to we just have to rescale, but by r eta, where eta is area under this function h. So we will use it for h we had before, so for this h, but it can be defined for h under some reasonable conditions. But if r is small, so then we can just approximate it using Taylor formula, and it is as follows. So it is initial value plus something times r plus O of r squared by Taylor decomposition. And if y is fixed point, then this coefficient should vanish. And it turns out that this ordinary differential equation for y is h given by this expression has a unique solution, which is the Verschuch's curve. So, so actually, surely it has many solutions, but just one of them vanishes at infinity. So just one can have unit integral not equal to infinity. And it actually shows that that this Vershkov's curve is a limit shape. And actually, this differential equation isn't very difficult, so you can write an explicit formula for solution for any function h. Okay, so I think I should stop.
Thank you, Yuri. Could I ask a short question?
Sure.
So you tell us that if we restrict ourselves to the nth floor, then we get the uniform distribution.
Yes.
And we know the limit shape for the uniform distribution. Is it possible to get the limit shape in your case along this line?
Along what?
Can we use this? Can we combine these two facts with some more estimates to get your result for the limit shape of your jump process? What do you think?
So I'm not sure what we can combine. What I think is that we can get some new proof of limit shape results. Actually, so what I tried to explain to you is kind of heuristic argument. I believe it can be done rigorously, and some kind of rigorous statement which we can hope to prove is as follows. So this growth procedure actually allows us to let's say some almost sure results about it, and I believe we can prove that almost surely if we consider our growing young young diagram and normalize it by square root of its size, then almost surely it will converge to a limit shape.
Okay, I realize that probably I don't understand a simpler thing. So you define the separators AR, and we get the limiting equation, and we have the Vershkov's curve as a unique solution. But what's the connection with the limit shape we're looking for? Why these particular operators?
So this when R is small, this particular operator somehow approximates this random evolution. So we have some random procedure of growth, and when we add when we ran it for a certain number of steps, say n to the power delta, then it is close to deterministic evolution. Now, this half-scaled Young diagram has order square root of n in y coordinate. We have scaled x coordinates, so but haven't scaled y coordinates. So if delta is smaller than 1/2, then this is still much smaller than d, because this is of order n to the square root of n, and this is of smaller order. And now what we do here, we do exactly the same as we should behave then. So we add this r, which is small, times deterministic function h, and then rescale arguments both in both directions by this 1 plus square or plus r eta, which is in U area. So y had unit area, we add rh, it becomes it will have area 1 plus r eta, and then we just rescale it to have a unit area again. And if r is small, it is a good approximation for what we had on a previous slide. So for this random procedure run from certain times when certain long time, but not very long, so that this randomness also already disappears by the law of large numbers. But r is still small because it is of order n square root of n divided by n to the delta.
Okay, I get it. Thank you.
Thank you. One more. Questions, comments? Yuri, could you send to me slides by email, please?
Okay, yes, sure. I will correct a couple of mistakes I saw and send it.
Okay, thank you very much.
One more short question. So after you get the limit curve, if we look at the local limits, it is almost independent, and it should be connected with the parts regarding the point process that you skipped, right?
Yes, so actually, yes. So what we do in our in this growth procedure, we everything which everything which happens with parts of different sizes is independent. So for different sizes of parts, everything behaves independently. And so if we are talking about partitions of certain numbers, then the only dependence which obtains is that the sum of parts is this number. So it's nothing. Everything else is independent.
Okay, thank you.
Thank you. One more? No.
Can I ask a question?
Yes.
Yes.
Yes, so back in the beginning, you talked about the uniform distribution. And you said that if we want to check that there is a process that leads to this uniform distribution, we have to check some inequality. And that inequality involved a subset of diagrams. So it seems to me that if you take this, if you look only on the subset of diagrams consisting of a single diagram, then you can check if it's true or not. Can you say something about that? Is it true?
Yes, yes, surely if you take A just one consisting just of one diagram, that it is true, because then this is a relative size of A, so it's 1 over P of n.
Yes, yes, yes.
And this is the set which can be produced from A by adding a box, and to each diagram we can add at least two boxes. We can so this is bigger than 2 size of A. It's not less than 2 size of A, whatever A of one diagram we take. But what is difficult here is that if A is relatively large, so actually for very small sets A, you can just realize that this is true. But for relatively big sets A and maybe somehow entangled in between, then
Yes, yes, I understand the problem. Yes.
Yeah.
Yeah, thank you.
Thank you for the questions. Okay. No more. Okay, let us finish now. The next